Greetings, Earth scientists, to our first lecture. Let's talk a little bit about the rock cycle and the importance of how it fits into our course. Rocks are all interrelated. As you walk around from place to place and you're driving from location to location, you'll probably start picking up rocks and not even noticing that you're doing this, but you're going to start automatically seeing a better history in that rock than you used to. So let's talk about where that history comes from, because the rock cycle is all about recycling. And recycling's giving a second life to something that it may not have had in the past. So some rocks have multiple recycling events, some have very few. Quite frankly, the ones with very few stories to tell of recycling are those that are more valuable in terms of interpreting the Earth's history. So the rock cycle shows the interrelationship of rocks, and basically it demonstrates that all rock materials on Earth go through a series of changes. They are either a sedimentary rock, an igneous rock, or a metamorphic rock. And I know you may be thinking, well, what about outer space rocks? That's a great question. These rocks actually end up in the same cycle because they end up on planet Earth. That's a small fraction of the rocks that we have on Earth today, but there's still one that we need to recognize. All right, you see what would be called a lava tube here. We'll be visiting that in lecture 2, but that's this structure right in here. This is a lava flow, and if you look at the red over here, you'll notice that there's a faint red underneath that cap. That's a lava tube. This would be an example of igneous rock. So rocks all start and originate in the igneous category. That will be a test question. So the rock cycle always begins with magma, not with lava, because magma came first. It's intrusive. You'll learn about that shortly. Once it gets to the surface, it can weather down into sedimentary rocks, which is this one steps right in here. If it hardens, it'll lithify. That's what lithification means. And then we might get a rock at the surface that gets metamorphosed once it gets buried deep enough in the subsurface of the layers of rock on Earth. So metamorphic rock is really cool. That's the interesting place in rocks, and we'll look at that in more detail soon. All right, so the rock cycle is all about a direction in which you move. I could start, remember, igneous rocks always start the rock cycle with magma, and here's your magma down here. And then see these little plutons right here, these are hot spots, and then you come here and you see the gray ones. Those would be cooled off igneous rock. So I can have two ways an igneous rock reaches the surface. It can either cool off underground, and let's just say that this particular underground is 30 miles beneath our feet. Or it could come up in the form of a volcano and erupt over here and produce a lava flow. Either way, I can get this plutonic rock down here or this lava rock at the surface via uplift and erosion. And now I have potential for them to be weathered and eroded and become sediments that could make sedimentary rocks. Sedimentary rocks get metamorphosed, let's say in a mountain building event. Or maybe I just want to get to sedimentary rocks and I end up getting broken down via a river or a glacier and I end up being another sedimentary rock. The point is, you don't go in a straight continuous line with metamorphic rocks. You're constantly cycling in and out of categories. So the full cycle does not always have to take place where it goes from igneous to sedimentary, sedimentary to metamorphic. You can kind of skip and go back a step or stay in the same category via shortcuts or interruptions. But we know that this constantly happens where one type, like sedimentary rocks, melt into igneous rocks, or igneous rocks get metamorphosed, or metamorphosed rocks get uplifted and then eroded and weathered into sedimentary rocks. This diagram helps show those pathways by which that happens. But remember, the rock cycle always starts with step 1, which is magma. All right, let's talk about the different types of igneous rocks. There are 2 types. There are those that are volcanic, and volcanic means the same thing as extrusive, X meaning above for the prefix. And then plutonic rocks are going to be like this one over here. They form as intrusive. The prefix in means inside. So which way you categorize an igneous rock, whether it's volcanic, extrusive, or it's plutonic, and intrusive is determined on where it crystallizes. So if it crystallizes inside the earth, we call that plutonic because it takes longer to cool off, so you get bigger crystals like these that you can see that are interlocking. That interlocking thing is going to be important in a minute. If I have one that cools above the earth in a lava eruption or some type of a shallow body, a shallow magma body like a sill or a dike, it will look more like this rock right here. These two rocks have identically the same chemistry. The difference is where they cooled off. So the one on the left is rhyolite, the one on the right is granite. It all determines on where they form and the chemistry by which they're made as to which category of igneous rocks that we put it in. So remember that rocks that form inside the earth, like these down here in the red, you can see all these different magma bodies. Well, the deeper you are, obviously, the longer it's going to take to cool off, especially if you're a large structure like this big gigantic red one down here. But notice on the cooled off side that's all black and gray, that's what it looks like once it's done and once it's cooled off. But we can get some of these that come up to the surface and make lava flows. Well, that would be volcanic or extrusive. So the one over here in Hawaii, from Hawaii National Monument there, Volcanoes Monument, that is definitely extrusive or volcanic. You can physically see it at the surface. So keep in mind that this magma chamber right here, let's just say it's a granite magma chamber. Granite is a special type of igneous rock called, it's felsic. In a minute you'll know what that means. It means it's high in silica. But when it erupts, it's going to produce a felsic eruption at the surface, and that's referred to as rhyolite. So the chemistry is identical, but the two ways the rocks look are completely different, and that happens to do with how long it took to cool off. So the composition may be the same, but the appearance of the rock will not be. All right, we classify igneous rocks based on texture, and texture is how do they look? How do the crystals look? Essentially, if they're interlocking, they have what we call a phaneritic texture. I always remember phaneritic for the P in phaneritic and the P in plutonic. So all plutonic rocks have a phaneritic texture. So what happened was, for crystals to get interlocking like this, they must have been growing over a long stretch of time, literally millions of years probably. Aphanitic, I always remember A for after the eruption. You're going to have a little bitty amount of time for crystals to grow against each other, so the crystalline structure is very tiny, if noticeable at all, without a microscope. And so we would call that aphanitic texture. So we're going to show you some of both. This would be a phaneritic texture. Notice the interlocking crystals. This is a good interlocking crystal matrix I'm talking about. The whole rock, if you picked one of these up, you've probably seen granite, and this is a form of granite right here, and that those crystals have grown all the way through the rock, so it's very, very dense. That would mean this has a phaneritic texture because it cooled slow inside the earth in a pluton of some sort. Plutons include things like sills, dikes, volcanic pipes, batholiths, and stocks and laccoliths. Aphanitic texture has 4 different potential personalities. So let me be clear, you can have an igneous rock that's volcanic that has no subtexture for aphanitic. It's just plain Jane lava. Nothing special about it. But most of the time, they have 1 or more different textures. So what I'm telling you is, you're not going to fit all igneous rocks into this perfect, nice little box that has just one kind of texture. Many times they'll have more than one, but they don't have to have any additional subtextures. So we're going to go through each type and I'll define them as we go. So vesicular means this. Do you see the bubbles that are in this rock? Those are called vesicles, and this forms because the lava has gas bubbles trapped in it as it is cooling at the surface. So these gas bubble cavities are left behind in the rock when the lava cools at the surface. This is an immediate dead giveaway that you're dealing with an extrusive volcanic rock when you have vesicular subtexture. This will not happen in plutonic rock. All right, the easiest one to recognize is this pretty glassy texture right here. Many students would think that this is one giant crystal, so they'll call it phaneritic texture. Just the opposite. This is what happens when you take silica, like sand, quartz-based sand, and you instantaneously cool it. This is how we make glass, actually, in manufacturing. So glassy subtexture means you had an immediate cooling of that rock, usually when it hits the air. So it's the best example of an aphanitic subtexture I can give you. All right, pyroclastic. The root prefix is pyro, which means fire. So you have to imagine if you get a pyroclastic eruption, that you get a big eruption, very violent. So not all volcanoes will produce pyroclastic subtexture because you have to have a lot of pent-up pressure to make that. So if you look at this piece of volcanic breccia, you can see that there's all kinds of material welded together. This is actually on truly a form of volcanic tuff here, more than likely, without holding the rock. And I took the picture, I can tell you it has characteristics of both. So this particular rock right here, you can imagine very explosive, the volcano falling apart at the surface with a really violent eruption, and that stuff adhering together because the materials coming out of the volcano were hot enough to sear everything and basically glue it together. All right, porphyritic. Now I want you to think about what I said earlier about phaneritic. And don't confuse porphyritic with phaneritic. Porphyritic is when you have a rock like this one. By the way, notice the vesicle, so this is extrusive right away, and notice there's no interlocking crystals, but there are some unique green crystals. First of all, this is olivine, known as peridote. Peridote's the birthstone of August, so happy birthday to you August folks. Now, neat thing about olivine is it forms only in the hottest magma chambers anywhere in the world. So there's only a few places we form it today in modern geologic time, and that would be places like Hawaii and Iceland. So what happens is you have to have this super hot magma chamber that when it crystallizes deep inside the earth, let's say 30, 40, 50 miles beneath your feet, it's hot enough to form this olivine crystals you see right in here, okay? But as that magma rises towards the surface, it never gets hot enough to remelt it. So that means that that igneous rock will contain these little crystal gifts when it erupts as a lava. And that's where the olivine comes from. So it's a two-stage cooling process. One for making the crystal inside the magma chamber. And second, it is the crystallization or hardening of the lava itself. So these end up being little gifts, and remember, they are not interlocking. That interlocking is only dedicated to phaneritic texture. So you can have no subtexture for aphanitic. These are absolutely personality, plain Jane, basic, nothing special aphanitic rocks, but they happen all the time. So if you see subtexture in an igneous rock, it simply helps you to put more clues to how that rock was formed. So remember, not all aphanitic rocks have the subtexture, but they can also have multiple types of subtexture occurring in the same rock, just like you saw with the vesicular basalt that had olivine crystals. It was vesicular and it was porphyritic. All right, which one is this? Is this aphanitic or phaneritic texture? Think about it for a minute. So does it have interlocking crystals would be my first question. If the answer is yes, it's phaneritic. If the answer is no, it's automatically aphanitic. So if you answered aphanitic, you were correct because this is instantaneous cooling right here. So this is instantaneous cooling right here, called glassy subtexture, otherwise known as obsidian. Does this have aphanitic or phaneritic texture? First question, does it have interlocking crystals? And you're like, well, no, it doesn't. So this is an aphanitic texture with nothing special in it. This is just plain Jane lava, rhyolite to be exact. Does this have interlocking crystals? The answer is yes, so it would be phaneritic. Does this have interlocking crystals? You're like, well, I see crystals, but they don't look like they're interlocking like the prior picture. You're correct. So this is a special type of aponitic texture known as porphyritic subtexture. All right, so we look at igneous rocks and determine how they form and put them in categories of types of lava and magma based on their mineral composition. And mineral composition is all based on the temperature ranges in which minerals crystallize. One of the main concepts in geology and earth science is to understand that all minerals crystallize and melt at different temperatures. So there was a guy that discovered this and came up with this theory, and his last name is Bowens. So we're going to look at the Bowens reaction series, and all that means is certain minerals react to certain temperature conditions, and most of those are pretty narrow windows of opportunity. So we only form those minerals at certain conditions, and you got to have those conditions present to make a rock. So in any textbook that you would read about earth science that has something to do with rock cycle, you will see this diagram right here. So let's start with olivine, since we showcased it a minute ago. Notice that it says very high temperature, first to crystallize. I think we said that, didn't we? And then let's come over here and let's look at the category of the composition. It says ultramafic, peridotite, and comatites. Peridotite is the magma, comatite is the lavas. We don't make these anymore because we don't have a hot enough Earth's interior to do so, like we did back in the Precambrian eon when the Earth was first made around 4.56 billion years ago. Keeping that in mind, let's take a look. Notice that I can form olivine at this line right here all the way to the edge of mafic. Matter of fact, I can form it to where the tip of the arrow is, right to here. So where I make olivine today must be somewhere from where my pointer is to the edge of this line right here, because it won't be ultramafic. Then you look at minerals like pyroxene and amphibole and biotite and mica. Notice they have narrow windows of opportunity, and they change if they're mafic, intermediate, or felsic. So the rocks you see, like for felsic, granite and rhyolite. Granite's the plutonic igneous rock with a phaneritic texture. Its matching extrusive volcanic rock is called rhyolite. The same would be true for the intermediate category. This would be diorite for the intrusive, andesite for the lava. Gabbro is just like granite in the mafic category, and its lava equivalent is basalt. So let's put some colors to these. Let's start with mafic right here. They're black or very, 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 very dark shades of gray. Now let's come to felsic, and I'll come back to intermediate. Felsic, notice that has a pinky color, and it's the reason is I can only form potassium feldspar, muscovite mica, and quartz in the felsic category. So potassium feldspar is pink, so you can have pinks, whites, tans, and very, very light shades of gray. That would mean if I have white, tans, pinks, and very, very light shades of gray, and then my basalt is black and very, very dark shades of gray, all other shades of gray must be intermediate. So if you find an ultramafic rock, they're beyond black. They usually have a deep, dark green tint to them. So Bowens reaction series is all about how magma cools and when minerals crystallize. So you can see the minerals that formed in this granite right here, and focusing on the background matrix, which is the background color. In this case, I think it's pink, which is potassium feldspar. Well, you just learned in the Bowens reaction series that the pink feldspars are only felsic. So this would be a felsic intrusive igneous rock known as granite. So notice there's some other minerals, hornblende, quartz, and feldspar. So if I had a matching extrusive equivalent to this rock, it would be called rhyolite. It would be lava or ash. So granitic rocks are what we just looked at. They are very high in silica, and that means they have lots of feldspars, a lot of silica and quartz. They're at least about 70% in most cases made of quartz. So granite's the intrusive version. The extrusive version of granitic rocks would be called rhyolite or felsic. The right term is really felsic. Basaltic rocks fall in the mafic category, and they are dark silicate minerals that are very, very rich in calcium and plagioclase feldspar, usually pretty high in magnesium and some metals, which means they're more dense. And so that's important because our ocean crust is made predominantly of this type of material, which plays an instrumental role when we get to lecture number 2, which is plate tectonics. I'll revisit that then. So the lava rock is basalt. The intrusive igneous rock is called gabbro. And gabbro looks a lot like granite, but it's pretty dark, pretty black. Somewhere in between, I have a rock that's pretty gray that comes into the intermediate category. You're looking at an intermediate igneous rock. By the way, do you see its crystals that are not interlocking? So this would be porphyritic texture. So this is porphyritic andesite. And they have intermediate amounts of silica. So depending on where you are in the range that makes up the percentage of silica for andesite determines how explosive the volcano is. So the closer you're to that mark for felsic, the more explosive andesite is. The further down you get closer to the mafic line, the less explosive that particular andesitic volcano will be. So when we classify igneous rocks, we can put them in these categories: felsic, intermediate, mafic, and ultramafic. Keep in mind we're only making these 3 right in here at the moment. And each one has an intrusive rocks, which would be these 4 right here. And each one has an extrusive lava equivalent, which are these 4 right here. Okay. So we've learned a lot about different textures of igneous rocks. Remember, they're either aphanitic for extrusive or phaneritic for intrusive/plutonic. So let's move into sedimentary rocks. Sedimentary rocks are made at the surface, but they get buried beneath rock layers over time. So they can go through a gradual alteration. So this is Green Sand Beach in South Point, Hawaii. This is actually made of all olivine, so that same stuff you saw in olivine basalt earlier makes almost 100%. I shouldn't say 100% because the beach studies on this actually prove that there's about 93 to 98% olivine. That's extremely high. And this green tinted sand is where it's coming from. So sedimentary rocks are so valuable to us because they help us reconstruct the Earth's history. So why are they important to us? Let's take a look at these coal seams. These black lines you see right here, these are all coal seams that were made millions of years ago. So there's a variety of different coals like lignite, what we have a lot in Texas of. Not very old, very young, usually about 50 million to 100 million years old. Then there's bituminous and subbituminous, and they can get up to several hundred million years old. Then there's the deep, deep buried coals called anthracite. And anthracite is very old, several hundred million years old, and it's had time to cook off the dangerous stuff that we don't want in the air. And subsequently, it's denser, burns better, has a lot of energy. So that's important, valuable resources to us for economic gain. Sedimentary rocks are usually pretty high in other types of deposits, including deposits of petroleum and natural gas, which are fossil fuels, just like coal is a fossil fuel, but they have finite resources. We can also find some metals in sedimentary rocks, which is very valuable to us for extraction purposes to use for building materials. So we categorize sedimentary rocks much like we do igneous rocks. They're pretty much 2 categories that we put them in to make it easy. They're either detrital, which is this word right here that I'm looking at right there. We can call detrital clastic because the root word of clastic is clast, C-L-A-S-T, and that means pieces and fragments of other rock material. So the common clastic rocks we have are things like shales, siltstones, sandstones, conglomerates, and breccias. Now, I can also have a different type of sedimentary rock called chemical, and that's this category over here. Chemical rocks are typically made by the dissolution of something or the precipitation of a mineral in seawater, rivers, lakes. That's typically how they form. And so the common 2 that you would probably see around here would be limestone, which can be converted into travertine in for example, a cavern setting, or you might see something like chert, which is made for arrowheads. You're like, I thought that was flint. We don't have very much flint here in North America, but essentially they're very similar rocks, and I have no heartburn about you interchanging chert and flint together. So here's an example of a detrital rock, meaning clastic rock. You can see some fossils in there. Don't be deceived by the fossils, but if you looked at this shale under a microscope, there'd be just hundreds of little bitty tiny microscopic clasts that are glued together with the cementation, and that's why it's detrital. It's a little hard to buy off on shale being detrital as it is compared to something like conglomerate, but nevertheless it is. You can see the grains easier in the sandstone, so you can buy off that that's detrital. You can see the detrital clast fragments with no problem in this conglomerate, but keep in mind, shale, which was the mudstone you saw with the leaf in it, is just as detrital as conglomerate is. Each one represents its own special way it gets made in depositional environment. So shale has to be very low energy environments for the little bitty tiny clasts to settle out and make large layers of that. Here, it would take a lot higher energy conditions to move the rock material, that all these different size clasts. So you would be looking at high energy flooding conditions from a river typically. All right, so the chemical sedimentary rocks are very different from detrital because they were once in solution and precipitate out. That means that they're not generated from the breakdown of other rocks. They're actually created by a chemical process. So the goods that make up the actual fabric of the rock come from a special chemical procedure. So common chemical rocks are limestone, chert, flint, jasper, agate, rock salt, gypsum, coal. These are all examples of chemical or biochemical types of rocks. This is fossiliferous limestone. That's a mouthful, isn't it? Fossiliferous. But you can see all the variety of animals that got buried in this limestone. That tells you a clue and a story right there of how the rock was made and the depositional environment by which it was made. Rock salt represents evaporating ocean water that was very salt, or lake water that happened to be salty. Every sedimentary rock, whether it is detrital or chemical, must go through a hardening process. And sedimentary rocks go through this hardening process where they're cemented, or undergo cementation, or they go compaction where you get the air out. So eventually they harden, and when they harden, they make a process called lithification. So that lithification word right here will be a test question for sure. What does that mean? So all sedimentary rocks are put into rock layers or beds, and over time many more beds will get stacked upon these. These rocks right here are from Arizona, and they come from a very famous rock formation called the Chenley Formation, and it's Triassic in age. So if you look at this, you can totally see the different layers and understand there's a history for each one. So when you look in sedimentary rocks, you can kind of just trace back what was living at the time, animal-wise. Was it from the ocean? Was it from a swamp? Was it from a terrestrial land environment? Was it from a desert known as Aeolian? So we can kind of help put that marker into a rock simply by looking at its clues of fossils. We can also tell something by the actual rock itself and how it was made. For example, sand grains that are in an ocean have a little water that act as cushions when they bounce together at the shoreline. But if you knock those same two quartz grains together with wind, you don't have that cushion. So what will end up happening is they'll cloud up like marbles that have smashed into each other. So we can use a lot of clues in rocks to help us determine how it was made. That's the value of sedimentary rocks. Let's move into metamorphic rocks because they're probably the most interesting but the rarest combination that you can find. In order to qualify as a metamorphic rock, there can be no complete melting. Let me emphasize that. No complete melting of a rock. You may have some minerals, since they all melt at different temperatures, which are fluidy-like. That's the magic of metamorphic rocks. So any kind of rock, including a pre-existing igneous, sedimentary, or even a prior existing metamorphic rock, can undergo metamorphism. A majority of metamorphism happens subsurface. On a very rare occasion, it can happen at the surface. So let me give you a surface example. Let's say we get a 6-mile wide meteor that smashes into the Yucatan Peninsula at Chicxulub, Mexico. Well, that happened at the end of the Cretaceous period and is thought to be a contributing factor for wiping out non-avian dinosaurs, which basically means dinosaurs as you know it. Okay, because avian dinosaurs still live with us today. That would be the birds. So do you think that if I had a 6-mile meteor smash into a beach that it could saute sand grains upon impact? And of course you'd be like, well, duh, yeah. So that would be an example of surface metamorphism. It happens very rarely, but it can. There are levels of metamorphic grade, and those grades are determined by how much heat and or pressure is applied to a rock, subsequently increasing the fluid reactions in a rock. So the lower the grade, the lower the temperature, and the lower the pressure has been applied. You can actually create metamorphic rocks with just heat. You can actually create metamorphic rocks with just pressure. But usually there's a combination of both together in order to make that happen. So there are two types of metamorphic rocks. Those that fall into the contact category and those that fall into the regional created categories. Then we'll look at their texture, kind of like we had texture for detrital and chemical for sedimentary and aphanitic and phaneritic for igneous. We'll look at the same textures for metamorphic. They have new names. Contact means that if you had for example, a magma chamber, and that magma chamber was heating up rocks around it, the rocks would get cooked and probably almost melted, but not completely melted. That would be contact metamorphism. Regional metamorphism is if you have a big mountain, like Mount Everest, for example, sitting on top of miles and miles and miles of sedimentary strata. You can imagine the immense amount of weight and pressure plus heat that can happen the further down subsurface that those rocks are buried. So they create large-scale changes to rocks that are called regional metamorphisms, typically associated with higher-grade metamorphic rocks with mountain building events. So the three agents, and this is a test question for metamorphic rocks, are heat, pressure, and fluid reactions. So obviously heat happens for every kilometer you travel in the subsurface deep. Let's say you travel 1 kilometer beneath the surface, you should increase by an average of 25 degrees Celsius. That's called geothermal gradient. That's an important concept. For every kilometer you go down, you increase 25 degrees on average Celsius. So you can imagine that just going down in depth can add metamorphism. The weight of overlying rocks is pressure. And if you have plate collisions, and particularly with subduction zones, that can create extensive mountain building. So between the two, pressure can do a real number on metamorphic rocks, and you'll see what I mean in a minute. And then once you get that heat and pressure going, some really cool stuff happens. And if you've ever been in science lab chemistry, you know that mixing different chemicals together can create some pretty interesting reactions. So in metamorphic rock, that certainly happens. So as you take a look at regular sedimentary strata like these, as a plate subducting or smashes into another one, it actually causes pressure to form against the crystals. And ultimately, here's your undeformed sedimentary strata. Now look what happens when it undergoes pressure. It changes the orientation of those crystals. So when that happens, you've applied metamorphic conditions to that rock. So there's two types of textures for metamorphic rock, foliated and non-foliated. So those are the equivalent texture terms. In igneous would be phaneritic and aphanitic, and sedimentary it would be clastic / detrital or chemical. So foliated texture we'll take a look at in a second, but it basically takes crystals and their random arrangement and kind of aligns them in parallel fashion. When that happens, that means that they're going to be perpendicular to the compressional force that occurs. You'll see what I mean in a second. Non-foliated looks almost like a mosaic of crystals all stuck together, almost like that phaneritic texture where someone took a soldering iron and glued with heat in between each one, where maybe some partial melting but not complete melting occurred. So here's a random arrangement before metamorphism of crystals in this rock right here. Look what happens when they get metamorphosed. See how they've been aligned perpendicular to the course or the pressure, and it gives it this kind of appearance. So let's look at the phaneritic texture in the granite over here on the left. Granite gets metamorphosed into a rock called gneiss. You heard me right, like a friendly rock, gneiss, but it's not spelled that way. And you see gneiss over here, and you can see it's made bands. Well, those bands represent the foliation that's occurred to a rock. So we have classifications of metamorphic rocks. If they're foliated, they're going to fall under the slate, phyllite, schist, or gneiss category, and these are all the foliated rocks. And it kind of gives you a description of the grains, how they pull apart or how they look, and then what potential parent rocks or rock they would have been before they got metamorphosed. Marble, quartzite, and anthracite are all examples of non-foliated rocks, and you're going to see some of the same kinds of descriptions there. So common metamorphic rocks you might see in the field. Slate is pretty common because it's low-grade metamorphic shales, and sometimes volcanic lava flows can do this too, and they split apart very easily like pieces of a loaf of a bread. So they cleave very well. Schist is strongly foliated, and it has a platy texture called schistostasy, and they can vary in their appearance, but literally most of these are beautiful rocks. They're very glittery because they're in that temperature range where we can form a whole bunch of mica and muscovite. This is a very common metamorphic rock you'll see associated with mountain building called gneiss. Check out the spelling right here, G-N-I-E-S-S. This is as foliated a rock as I think as you'll actually see, because there's still one more metamorphic rock beyond gneiss that's foliated called migmatite, but it's so rare because it's really at that melting point, so you don't see it very often. So non-foliated rocks, if you look at this, you don't see any arrangement in a parallel fashion of grains. Instead, the grains look like they've been glued together. There are two major non-foliated rocks I think you'll see regularly, marble and quartzite. Marble's parent rock is always limestone or dolostone, so it's pretty soft because the hardness of calcite that makes up limestone is 3 of the most hardness scale. Quartzite is made up of a much harder mineral called quartz sandstone, and quartz has a hardness of 7. So it's a relative scale, Mohs hardness from 1 to 10, with diamonds being the hardest and talc being the softest. So with that thought in mind, you need to think about which one would take longer to weather. Would it be the marble or would it be the quartzite based on its hardness? And if you answered quartzite, you answered correctly because the quartzite's harder and more durable than the limestone. So we get a lot of mineral resources that come from rocks, whether it's igneous, sedimentary, or metamorphic. And some really incredible stuff happens in igneous and metamorphic rocks where we can add heats and fluids and chemistry to create things like metals and gemstones and precious resources that can only be made with heat involving material. Things I can think of would be some of the ones you see here: gold, silver, copper, mercury, lead, aluminum, things of that nature. Most metallic minerals can be made through some kind of heat process, including hydrothermal processes, which would be related to things like geysers or caverns. So oftentimes we'll see deposits of rock or metals or minerals that form along hydrothermal vents, deep sea vents, or in geyser region areas. You'll see unique minerals that are used for economic gain that get made in those special situations. Non-metallic minerals are typically made by just sedimentary processes, sometimes by igneous or metamorphic, but most of the broad categories that we use are building materials. Things like limestone or sandstone or shale, and in the mineral departments, things like corundum or sylvite, fluorite. These are all things that have industrial uses, and you may not even think about that. You're like, well, I just hadn't really thought about that. So minerals actually have a very important role in dollar signs for us. So you look at this kind of in a table format and you start to see how much stuff we use. Sedimentary rocks definitely get the blunt majority, and the reason being is the stone that's available at the surface is sedimentary and most of it is easy to get to. And not in all cases. We have some that are non-sedimentary like granites that we use for building stone. But since so much of the Earth's surface, 75% of it is covered with sedimentary rock, we have a lot more sedimentary rock to build with than we do igneous rock or metamorphic rock. So you look at the metallic processes and see how much smaller they are in volume compared to non-metallic resources, which is one reason that metallic resources have a higher intrinsic or dollar related value. Then don't forget about the energy resources. They're responsible for what's making your computer go right now. Fossil fuels, while they may be finite, are extremely important to you, and as we deplete them, renewable energy resources need to become important to you. So to sum it all up, let's go back to the very first thing you saw, the rock cycle. Remember that the rock cycle always starts with this thing right here, which is magma. You got it. But it can go in and out of any pattern of sedimentary, igneous, or metamorphic. The key is to understand that rocks are constantly in a state of change and they're being recycled, those materials, over and over again. So there's a history for each and every rock that you see at the surface. I'll see you at the next lecture. Bye.